Okay, here's a thought for you. What in the world could possibly connect an ancient potion that promised eternal life, the age-old dream of turning cheap metal into gold, and, of all things, the battery that's powering your phone right now? Well, the answer is a story that's been unfolding for thousands of years.
It's all about chemistry. You know, that incredible, relentless human quest to figure out what our world is actually made of? From the things we see every day to the wildest ideas we can dream up.
So in this explainer, we're going to follow that amazing story, all the way from the magical ideas of alchemy to the mind-bending reality of the atom.
And our journey starts, as so many do, in the ancient world. A time when people were asking these huge, almost mythical questions and taking the very first steps toward real, practical science.
For centuries, a lot of this early work was driven by two incredible dreams. First, you have the Philosopher's Stone. I mean, just imagine it, a substance that could turn ordinary, worthless iron into pure, shimmering gold. And then there was the Elixir of Life, a potion that could make you live forever. Now, these might sound like fairy tales to us, but for the alchemists, they were the ultimate prizes, and they sparked thousands of real-world experiments.
But while the alchemists were chasing those big dreams, another story was unfolding. Over in ancient India, a really practical science called Rasayan Shastra was already booming. We're talking way back in the Harappan civilization, where they were mass-producing baked bricks and beautiful glazed pottery. Fast forward a bit, and you have texts like the Rasarnavam, which describe super advanced furnaces and even a technique we still use today, identifying a metal by the color of the flame it makes. This was chemistry in the real world, used to create everything from glass and construction glues to soap.
For a long time, chemistry was kind of chaotic. There were tons of reactions and different substances, but no single idea to tie it all together. It needed a rule book. And that revolution came from one man with a simple yet incredibly powerful idea.
So in 1808, John Dalton comes along and basically lays down the law. He said, okay, everything is made of these tiny, unbreakable particles called atoms. That's rule number one. Rule two, all the atoms of one element, say gold, are exactly the same. Rule three, compounds, like water, are just atoms from different elements combining in simple fixed ratios. And that means a chemical reaction isn't some kind of magic. It's just atoms shuffling around and finding new partners. For the very first time, chemistry had a clear set of rules.
Now, Dalton's theory was a total game changer. It explained so much, but there was this one huge nagging question. If atoms are just these tiny, solid, indivisible billiard balls, then what about electricity? Where does something like static cling come from? It was a major hole in the theory, and it meant there had to be something else going on, something inside the atom.
And that one question is what pushed scientists to look deeper, to actually try and peek inside that supposedly indivisible atom. What they found would change everything, revealing a whole new world of particles smaller than they ever imagined.
The first real crack in Dalton's perfect little billiard ball came in 1897. A physicist named J.J. Thomson was experimenting with these strange beams called cathode rays, and he discovered something incredible. These rays were made of particles that were way smaller than an atom, and they had a negative charge. He had discovered the electron. And just like that, the atom wasn't indivisible anymore.
This, of course, led to a new puzzle. Okay, so atoms have these tiny negative electrons inside them. But we know atoms are neutral overall. So where's the positive charge to balance it out? Thomson took the first logical shot at an answer with his famous plum pudding model. He pictured the atom as a big, fluffy ball of positive charge, that's the pudding, and scattered throughout it with a little negative electrons, like plums. It was a neat idea, but it was just an idea. It needed to be tested.
So how do you test a model of something so small you can't possibly see it? Well, one of Thomson's former students, Ernest Rutherford, came up with an absolutely brilliant experiment. He decided he would shoot tiny, positively charged bullets called alpha particles at a sheet of gold foil that was incredibly thin. The thinking was, if the plum pudding model was right, those positive bullets should zip right through the soft, fluffy pudding of the gold atoms without any trouble. And what happened next was one of the most shocking moments in the history of science. Just as expected, most of the particles flew straight through. But, and this is a huge but, some of them were deflected at wild angles. And even crazier, A tiny fraction, about 1 in 20,000, bounced straight back as if they'd hit a solid brick wall. This was absolutely not supposed to happen. The plum pudding model was dead.
Rutherford was stunned. He later said it was like firing a cannonball at a piece of tissue paper and having it come back and hit you. He realized there was only one possible explanation for this. For a positive alpha particle to be knocked backward so violently, all of the atom's positive charge couldn't be a soft pudding. It had to be crammed into an incredibly small, dense, hard little nugget.
This led to a totally new and, frankly, mind-bending picture of the atom. It wasn't a solid ball at all. In fact, an atom is almost entirely empty space. All the positive charge and almost all the mass is packed into a tiny, dense center that he called the nucleus. And the little electrons, they were orbiting that nucleus from way, way out, like tiny planets orbiting a sun. But here's the thing about science. Every new answer creates a new question. And Rutherford's beautiful new model had a huge, fatal flaw that just didn't make sense according to the physics of the day. Solving it would require a leap that was even more radical.
So what was the flaw? Well, according to the laws of physics as they were understood then, an electron whipping around a nucleus should be constantly giving off energy. And as it loses energy, it should slow down and spiral inward, crashing into the positive nucleus in less than a second. Basically, every atom in the universe should instantly collapse, but obviously, they don't. The world is stable. So why?
The answer came from a Danish physicist named Niels Bohr, and it was a real head-scratcher. He essentially said, what if the old rules of physics just don't apply inside an atom? He proposed that electrons weren't free to orbit anywhere they wanted. Instead, they were locked into specific fixed energy levels, or orbits. It's like a ladder. An electron can be on the first rung, or it can jump to the second rung, but it can never exist in the empty space between the rungs.
And this model was a spectacular success. At first, it perfectly explained why the hydrogen atom gives off its own unique pattern of light, and it gave us this incredible idea of a quantum leap. But it had its own problem. It only really worked for hydrogen. As soon as you tried to apply it to more complicated atoms, it fell apart. So it wasn't the final answer, but it was a hugely important step that pointed the way toward the even weirder and more wonderful world of quantum mechanics.
Okay, so we've journeyed from plum pudding to tiny solar systems to quantum ladders. But these weren't just abstract ideas for physicists to argue about. These atomic blueprints were the missing key that finally let us understand how atoms actually build the world we live in.
And the real prize was understanding the chemical bond, that fundamental force that glues atoms together. Once we understood how electrons filled up their shells, or rungs on the ladder, we could finally start to predict how and why certain atoms connect to form all the molecules that make up, well, everything.
And it wasn't just about building things. It was about powering them. Scientists quickly figured out that every single one of those chemical bonds holds a certain amount of energy. Understanding that energy, how much it takes to break a bond, and how much is released when a new one forms, that's the secret behind thermodynamics. It explains everything from why a fire feels hot to how a battery stores power. So when you trace it all back, you see this incredible line. From an alchemist's furnace filled with hope and smoke to Dalton's neat and tidy rules, all the way to the strange, beautiful quantum dance inside the atom. This journey of discovery isn't just a history lesson. It's the absolute foundation for modern medicine, the materials in your house, and the technology in your pocket.
Each time we thought we had the answer, we found an even deeper, more interesting question waiting for us. We've come all the way from alchemy to the atom, and the journey is far from over. It really makes you wonder, what's the next great mystery that chemistry is about to solve?